all class long. So feel free to add whatever you think can enhance the learning opportunities. Now, is the lighting okay, or do we need this front light off? You want to see what it looks like with it off, and you be the judge. Is that better for you? Yeah. Plus, it gives you enough light in order to write? Okay, excellent. All right, Module 14. So, wow, you all learned a lot in that last 5 minutes. Modules 1 through 13, you've already covered goddamn pat. Wow, you are good students. Module 14 deals with groundwater production. And so at the end of this module, it is our hope that you will be able to at least discuss how groundwater is made usable. Now, for some that may have private wells, you may say, well, the only thing I do is pump it out and go. Because the truth of the matter, where I grew up, I'm originally from Mississippi. We were not on a city system. We were on a cistern, which was rain catchment. And literally it was just, okay, pulling the water out of the cistern, picking out the leaves, and the granddaddy long leg, I don't know what you all call them. Yeah, with no boiling, nothing. Now, how dangerous was that? After I got into this field, it really freaked me out because it was like, oh my goodness. It was just sedimentation was the only type of treatment that was, done. What if some type of pathogen had been in that water? And so it became, this was very interesting field for me because it was something totally different from the way I had grown up. Our enabling objectives, our terminal objectives, of course, is to make sure that we know how groundwater is produced, made usable. How or what will get us there is that we're going to look at various types of groundwater, mainly aquifers, which are the underground water-bearing formations. And we're going to look at what types of aquifers, whether or not they're shallow wells, deep wells, artesian wells. We're going to look at springs, which is another source of groundwater, and how they differ, and what type of treatment may be required based on, again, where this water comes from. So we'll look at common methods of groundwater treatment. Now, currently in Kentucky, what must you do as far as groundwater, as far as treatment? What is, okay, so disinfection is a requirement, state requirement. Anything else? Well, as far as requirement, because I know it will always go back to the quality of your water. For instance, if I have iron and manganese, I may have to do something additional that may not be a state, blanket requirement. Fluoridation is one that's usually state mandated. So do you all have fluoridate? No, your water?
Yeah,
and some.
Based on population.
Okay, based on population.
I was threatened by Murphy that if I tried to stop fluoridation, I'd be in some big trouble. Even though our system is small enough that it's supposed to be voluntary.
Who's Murphy? Murphy fluoridation guy.
Yeah. Health department. I hate that
Okay.
Kenny left. Dealing with him.
Give me a call, and I'll check.
He said that 35 years ago, somebody that worked for the system signed that they would fluoridate, and that's a binding forever contract. That's what he told me, and told me I would be in some big trouble if I tried to do it otherwise. So I just dropped it.
Okay, that's good. That's a good thing that training like this is available, so you can voice that and they can investigate and get back with you as to, what's the real deal on that. So training can be helpful in a lot of ways of bringing out those misconceptions that we may have at one level that they may be clueless up here as to where did you all get that information from? But yet it's something that we take and we take it as law, and it may not be such. So excellent. So hopefully you can get some type of response on that. So we're going to look at common method. Now basically it's going to go back to the quality of your water. But common method would be sort of like disinfection, and we'll cover that over a 2-hour span this evening. Okay. Now, groundwater, unlike surface water, has been filtered through the various levels of soil, correct? And it is usually a universal, I guess, approach that because of the filtration that most of the impurities are removed, correct? As far as organic. Do you all believe that to be a true statement? Are y'all going to be this quiet on me? Yeah. Yeah. Somewhat true, because we do get the filtration process going on in groundwater. However, there may still be possibility of contaminants in groundwater. And I know a lot of times we buy those bottled waters that says from the sparkling springs, it's just groundwater that's reached the surface. It too may contain some form of contamination that may be, again, very, very critical for us to remove in order to make it potable, ready for human consumption. And so although well water may be clear, sparkling, and yet contaminants may endanger the water, which may cause ill health effects. Yes, sir?
One water class I was in, the instructor said, well, if you buy bottled water, do not buy spring bottled water. How do you feel?
How do I feel? And this is personal.
Yeah.
Okay, totally personal. It depends on the process of treatment of that bottled water. And that's...
All you have to do is go through two treatments to be classified as bottled water, correct?
Now, again, they're not as heavily regulated, so I'll always go back because really they don't have to go through any type of treatment per se. If it's an RO system, reverse osmosis, I feel pretty good about that water, but it's essentially dead water. But as far as impurities, once that cap is broken, if there's any bacteria that's introduced in that water, there is no disinfection available to combat the growth that may be occurring there. This is me personal. So
spring water would be the same as normal. This guy's
Yeah.
because spring water basically said only go through one filtration process and other water go through two.
Yeah, I like the fact that public water must disinfect because the disinfection will destroy. It may not kill everything, but most of the pathogenic organisms are kind of taken care of with the disinfection process.
So you're saying municipal water is safer than...
Of course I'm saying that because I'm a proponent of it. But again, it gives you a greater sense of security with that chlorine in the water. Yes, ma'am.
Just a side note on that, with the bottled water, isn't it different from state to state, just like
It is.
treatment? And so when you're buying the
It's
bottled
not
water,
regulated.
you don't know where it's treated. Like here in Kentucky, bottled water systems still have some of the same regulations as...
So you all do regulate it.
We do regulate them. I
Okay.
mean, it's still different, but there is a level of regulation for the bottled water systems, but that's different in other states.
Absolutely.
And if you're not familiar with the regulations for that state, you don't really know what kind of product you're getting.
And where that water is being shipped
They
in.
come across state lines, they still have to meet our record, right?
Mm-mm.
Okay, so then if it says it's made in New York City, then...
And just because it says spring on the bottle doesn't mean anything, because like Tyler out there was called Mountain Valley Spring Water, and they bought the water from West McCracken, which
Yeah.
comes from the river.
A lot of times there is a line that runs right to that bottled water company. It's already been treated by the city, and they're taking the same water that you've already paid for it, processing as far as the bottling, and now you're paying, an extra. Do you know how much you probably pay per gallon for bottled water? Anybody have an idea when you're buying those individual bottles? Huh?
Isn't it something like $100 a gallon?
Oh, no, not quite that much. Wow, we've really broke. But it's about $11 or $12 a gallon. That's a lot. You don't even pay that much for gas and you're crying about it. So that's a lot. So something to think about. We want to make sure, again, we instill confidence in what we're doing in this field. And we're doing a doggone good job at cleaning the water up, if I must say so myself, Chuck. How many people do you have just dying off or getting terribly sick because of the water you're producing over the last couple of years?
We all gotta say none, or else we would be in trouble.
No, you won't be in
We
trouble.
got those people back there, they're all watching us.
But you do, and they would know about it. Probably probably before the public, but we do such a wonderful job with cleaning the water up. And it's safe to drink. So if you're doing it just because in fear that public water may not be as good, know that it is as good. But if you're doing it for convenience and you just got lots of money to spend, go for it. Yeah.
I feel confident what we do, but it's we go elsewhere.
Yeah.
That's,
And there are different, what I have found out, as especially through my travels, from state to state, regulations are different. But the beauty of it is that we all fall up under the EPA umbrella, which means we have to at least meet their minimum requirements, which again gives some sense of confidence there. Now, some states may love you a little more and be more stringent, and I have found that the case. Texas is one of them. Guys, they are so much more stringent on a lot of different things. But that's based on the quality of our water. And that's what you will typically find from state to state. Okay. All right, good question. All right, so sources of groundwater, protection of the public health is always first priority. And that's exactly what you all have been talking about now, even with the ground versus the bottled water. Ultimately, that's what we're most concerned is producing a product that will not cause any ill effect to our consumer. Potable water must not contain harmful amounts of disease-causing microorganisms, and we'll talk about some of those disease-causing organisms, or chemicals, or even radiation. So we want to make sure that none of those issues are there. When they are and are naturally occurring, then we have to do additional treatment, or we may have to find different sources of water. We actually had a facility in my early years that had a problem with the radium-226, 228. It was naturally occurring in the rock formation that was there. So they had to abandon that well, dig another well. And in the meantime, we had to provide bottled water to our consumers because ultimately it's about public health. So, groundwater is usually well filtered, as we said before, and again, due to the layers of soils, slow percolation through the earth material, usually very, very, very little turbidity, which is a major problem with surface sources, should be little amount of color as well as organic matter there. However, because rocks, soil, mineral in content, water is the universal solvent. So as it percolates down over those medias, what's happening? Anything that's in that rock can be dissolved into the water. So generally groundwater is higher in dissolved minerals or total dissolved solids, more so than surface water from the same area.
water, you can gain weight.
Gain weight? Now what minerals putting weight on you?
There could be some bunch of stuff in that water.
Yeah, that's a new one. I'm going to have to go research. Can inorganic things actually add weight to you? I do know that our bodies need them because how many of you all take a multivitamin? Yeah. Just drink your water and make sure all the impurities are there. You'll be fine. No. I often used to tease a customer is that you don't need the iron pill because we're giving you enough in the water. But again, those scenes are aesthetically probably not pleasing to our customers, and we want to produce a product that is aesthetically pleasing, so definitely we're not sending our consumers red water. We're going to sequester or remove it out. And it can also cause other problems when you have other minerals or metals in conjunction there. It can create health issues. So those are some of the things when they exceed the maximum contaminant level. If it's on that list or the secondary contaminant list, we're going to make sure that we have things in place to remove. Now, groundwater is simply underground water-bearing formations. We refer to them as aquifers. They will occur at different depths throughout the United States. There are some, one that I discovered actually comes all the way from Nebraska down into the Texas area. So again, they can be very widespread from state to state. Useful quantities of waters are the ones that we're going to tap into because there are some aquifers that may not yield enough water to amount to anything. So we're looking for the ones that will yield useful quantities of water for public supply. Now, is it possible to withdraw too much water from an aquifer? Absolutely. And in Texas, we're experiencing that. And because of that, we're being, I won't say forced, or we're being mandated to go to surface sources. So it is possible. Usually your groundwater or aquifers will contain more gases, dissolved minerals, but fewer microorganisms than surface water. However, we're going to talk about what if all of a sudden every time it rains, I start to see organisms in my groundwater source, or there's a shift in pH or alkalinity. What is that telling me about my groundwater source? It's under the influence of surface water. And whereas you all told me earlier, your only mandated treatment for groundwater is disinfection. However, when you look at the mandates of surface water, there are several required treatment processes that you must employ. So if you find, you've done the survey and you see that your groundwater is under the influence of surface water, then that puts you in a different bracket of treatment processes. So these are some of the major aquifers in the United States. What's one of your major aquifers here in Kentucky? Let's see, where are you all? You're somewhere up in there?
Nice looking purple one.
Huh? Nice looking purple one, which is, you couldn't tell me?
Sort of yellow.
Down here, it's the Claiborne group.
Okay. So where is Kentucky? About right in there? Yeah. Figured that. Well, that major yellow one there is the Gulf Coast. I can tell you that because it's in Texas. I know about that one. Your major one here?
Well, I don't know actually the name of the formation itself, but the aquifer itself, but the formation consists of formations in the Claiborne group.
Okay.
15 sands.
Okay. Okay, excellent there. And then you may have some minor ones also that you're retrieving your water from. For those that are following along, we're on 14.4. Now, as far as how much water you're going to be able to retrieve from any aquifer, it'll go back to the porosity of the percent porosity of the formation. In other words, if I have limestone with large fractures, then those are large pores, versus sand or gravel, which again, you have pores because they're not going to fit together. So porosity or percent porosity has a lot to do with the pores in your formation. Clay, on the other hand, may not be as highly has porosity. It'll also depends on the specific yield, which is the quantity of water that can be drained from the formation. Let's look at clay versus sand or gravel. If I poured water onto clay, sand and gravel at the same time, which one do you think will yield more water, or water will flow through more easily? The sand and gravel. Very good. So with clay, although it may have lots of holes from time to time, it's going to hold on to or retain the water. It's not going to give it up as readily as the gravel or the sand. So specific yield will go back to how much can be drained. Specific retention is the amount that's retained, and the permeability is the capacity of the formation to transmit water through it. So we have springs, which are groundwater sources that reach the surface. We have water table wells, and these are aquifers that are not overlaid by an impervious layer. This one here, aquifer here, will be a water table. We also refer to those as your very shallow wells. And we have artesian wells. With artesian wells, they are usually overlaid by impervious layers as well as impervious layers underneath. Now, if you have impervious layers on top, like the shale or the granite underneath, what happens to that water when I tap down into that aquifer? Squeezed by pressure, it's pressure. So it will do what? It will rise to the top, absolutely. Now, not all confined or artesian wells, not all of them are free-flowing. And of course, springs, again, would still be the outcrop of your aquifer, just the fact that it reaches the surface. That's the only difference in a spring. It is considered groundwater. And here, they kind of show you also porous limestone, again, is the ability of water to be transmitted through the pores that are present there. Here, you don't have all these pictures in, but just to give you a better idea of the different formation. Here again, we have a water table well. It is not confined. Here you can possibly have the intrusion of surface water into that unconfined water table well. This one here is one that is confined by a top and lower level there. This one also shows, again, recharging of the aquifer from, again, precipitation. And that's how a lot of time recharge will occur. And this would be a confined, again, where you have the various layers confining the water itself. Okay. So the thickness is the vertical distance in feet from the top to the bottom of the formation. And as you can see on figure 14-2 on page 14-4, some of those aquifers literally cover several states as far as the shading. The yield is dependent upon the porosity, the permeability, specific yield, and thickness. So as Rob pointed out, there was a little more involved than just those two that was on the exam, but it's still true because it does, I think it says the thickness and the permeability was the two that was specified on the exam. There are a lot of other things that go into that porosity, how well it gives up the water or not give it up or retain it. All of those are factors in determining the amount that the aquifer will yield. Okay? Now, as far as, I don't want to go there yet, groundwater withdrawal, under well location, that's where we are now. When you dig a well, there is an area that is dewatered during the process, and that is called the cone of depression. There with your deep artesian wells, it is called the zone of pressure reduction. You want to make sure when you're digging wells, you're not digging them too close together where their surface of influence or radius of influence overlap. Now, what will happen when you have two wells that are too close together and their circles overlap? What will happen to your gallons per minute production? It's going to drop, absolutely. So that's one of the things that you want to take into consideration as far as the digging or the location of your various wells. As far as how many feet apart they should be, no, not from EPA. Yeah. But you want to keep that in mind depending on how much you want to yield. Now, earlier you all caught this. Static level is that level of water, that natural level of groundwater with the pumps not running. Okay, that is your static level. Once your pumps come on, what happens to this level? drops down, right? Because now you're pulling the water up here. So with the pumps on, it is referred to as the pumping level. It's going to drop. The difference between the two, the pumping and the static level, is the drawdown. And again, you want to minimize the overlapping or keeping your wells too close where there's circle of influence. And again, when you look at the radius or surface of influence, you're looking at from that well to how far it goes out. If their circle of influence overlap, which there may be just a little overlapping right here, then the amount of withdrawal will be reduced from those wells. So keep that in mind when locating your various wells. All right, static level, pumps not on. Pumping levels with the pumps running. Drawdown will be the difference between the two. So that's pulling the water out, and actually I'll go step by step a little later on actually digging the well. This is just still the overview point right now. So we got the water out, and earlier I asked the question, is it possible to pull too much water out? And you all told me yes. Aquifers are recharged by one or two ways, either natural recharge or artificial recharge. Natural recharge we're dependent on who? Mother or Father Nature, okay, in order to produce the precipitation. How long does it take for that to percolate down into my groundwater source? Could take a long time, absolutely, especially depending on the soil type that I have. How long it may take weeks, it may take months, in some cases even years, depending on the depth of the aquifer. But it is still recharged by rain, snow, seepage from lakes, and rivers. So that will be our natural recharge. But it's going to be dependent on the type of soil, the nature of the terrain, ground vegetation, as well as the intensity of the rainfall and the seepage drainage. So it's a lot of things to contend with in order to replenish what I've withdrawn, because the truth of the matter is I'm withdrawing it at a fast rate. And I don't know about you in Kentucky, but a lot of times we are very much under the required rainfall and usually in drought mode for most of the spring and summer in Texas. So that will be natural. Artificial recharge is we have planned or we have unintentional. With planned, we have spreading grounds, infiltration ponds, sewage treatment plants, spreading grounds, and recharge injection wells. In other words, and this is true for Texas, we have areas where we take treated wastewater, and yes, I did say treated wastewater, and inject it back into the ground for it to continue with the filtration prior to reaching the aquifers. Do you all have recharge zones down here?
Do they consider that surface water then, under the influence?
No, we don't. It's not, because again, from a treated wastewater plant, it may have come from any source, but it's still considered groundwater because it is being filtered through several layers or feet prior to reaching the aquifer. So it's still considered groundwater.
So it's not injected directly into the aquifer?
No, not directly. Yeah. Good question. Because that's how much we're pulling it out so fast. And I often tell people, and we need to get to that mindset where it can be flushed today, table tomorrow. Think we'll ever get there? That we'll be that good? Turn it around. There are pilot programs. Yeah.
No instances of contamination for that process?
Huh?
No instances of contamination from that?
Then when you say no instances, of course our goal is always zero. Does anything ever occur? I'm pretty sure, just the same with the treatment we received today. If you are on a surface source, what do you think you are treating?
What do you mean? I'm sorry.
Okay, if you're already on a surface source, what's in that water already?
Oh, you're doing the organics and the microorganisms.
Where do all our wastewater discharge into?
Oh, yeah.
Our surface source. So I often tell people in Texas, we're drinking Dallas wastewater. It flows, as Wayne says, downhill. So where we're retrieving for our drinking water source, a lot of wastewater treatment plants are dumping into there. That's why it's so critical to get it right on both sides. Remove it on the wastewater side so it's not as difficult on the water side. So we're already there. There's just a longer turnaround. It's not flush today, table tomorrow, but that's exactly what we're doing anyway. How many of you all have been keeping up with the other issues that's in surface water, such as if I'm on medication, and I am, and if you're on medication, guess what? We're drinking each other's medication. Yeah. So those are issues that we're already dealing with and that we're getting it right. So that would be planned artificial recharge. Unintentional would be irrigation or your sewage treatment plant effluents, septic drainage fields, leaking septic systems that gets into it. And that's an unofficial way of recharging the groundwater. And of course, it's one way that we don't want to occur because we have very little or no control over the contaminants that's being put into those groundwater systems that way. Man-made reservoirs. And that is the reason why when we look at, again, the sanitation distance for our wells, that as far as your sewage treatment plant effluents, more than 500 feet away. And that's to minimize direct contamination of our groundwater sources. All right. What is happening here? It is a sinkhole. And you know where I found this sinkhole? Bowling Green, Kentucky.
When was that?
Overpumping. Oh, now you're asking me to remember too much now. I can't remember what year. There was a year when I pulled it, but I don't remember what year it happened. Overpumping leads to subsidence, and more and more and more. We had a major one in the Houston area. More and more and more, we're seeing sinkholes. A couple of weeks ago, where was that guy? Florida, yeah, in his bedroom, yeah. So again, there was one on the,
Playing golf and a sinkhole, director, like you say, underneath him.
a little louder so they can hear it
He
back
was
there.
playing golf and stepped on an area that was a sinkhole and fell 18 feet.
Wow.
And it took him about half a day to rescue him out of it.
Mm.
Lives in Illinois.
But he was rescued. That's good. Yeah. Yeah, so overpumping is a problem. And it's a problem that, again, that is beginning to kind of go beyond just your little state or my little state. So we're going to have to start looking into alternative sources. Do you all have a problem with overpumping with groundwaters here? No, right now it's not yet. All right, so how do we construct a well? How do we dig a well? Types of wells on 14.7. In the past, small wells were dug by hand. And I do mean very small wells. They can be bored by an auger or driven with a percussion drills or jetted using water pressure. But the most common methods for developing wells today is your rotary drill. And again, we have different types of bits based on our soil type. So that's what our rotary drill. Rotary drilling uses a rotating bit for cutting a borehole and then continuously circulating the drilling fluid, mud, to remove the cuttings, and that's usually removed back up to the top in a mud pit or what have you. Bentonite clay It's used as a drilling mud, and that's pumped down the hole by positive displacement mud pumps. And again, just to give you a little more information in the book, give you what some of the bits look like based on your type of material that you have to go through in soil. So we have the bit, we have the drill collar pipe, the drill pipe, and the Kelly. At the bottom, and we'll talk about the various type of construction method. We'll also talk about well construction, various parts of the well. We'll look at the gravel pack. So when we talk about the gravel pack, that's what we're talking about at the bottom of that well. Works began there. So parts of a well, we have the well casing, 6 to 36 inches in diameter, standard weight. Steel pipe, it can be plastic also. So a lot of different materials can be used for that. Carbon steel, high strength, low alloyed steel, stainless steel, plastic. You want to make sure that it is conforming at least to the AWWA standards, which is the American Water Works Association. It should extend to the top, from the bottom to the top first part of the impervious layer to at least 18 inches above the natural floor of elevation. And it will be cemented in place in order to keep the well from collapsing. So it protects it for collapse. It also prevents surface contamination. So we have the upper formation, impervious formation, water bearing, and that's what we're trying to get to. So when we are putting this casing into place, we're going to put in a pilot hole initially, which will not be as large as the casing itself. You'll then increase the hole diameter, and then after that, we will put the casing in from the surface. Okay, there goes the casing coming in. It is installed in the enlarged hole. Again, it's going to extend down to the water-bearing formation to at least 18 inches above. After the casing has been put in, we're going to now apply the pressure cement in place. And the purpose of the cement is to do what? Super. So that's our little hole to put the pressure cement. The blue is the cement. So we are cementing that casing in place. Okay. Underreaming. So this is beneath it. We have the cement, we have the casing in place. Now you want to make sure, again, that we drill another pilot hole, because now around there we're going to put the gravel pack. Enlarge the hole. We're utilizing the drilling mud, the bentonite clay, to install the well screen next. What is the purpose of the well screen? So we have the casing, we have the cement. Now in the actual water-bearing formation, we're going to put a screen down there. Now, was the purpose to keep out birds and insects? No! Fossilize those. I had one group that wanted to argue with me, but there's a screen. Yeah, there is a screen on the vent up top, but the well screen at the bottom is, the main purpose is to minimize the pumping of sand. Yeah, because that can do wonders with your pumps, right? Yeah, so it's to help keep out the formation of sand. So your screens can be slotted, drilled, extruded, or wound, spiral. It can be made of bronze, plastic, stainless steel. You want to make sure you're getting a material that is non-corrosive, because groundwater, some groundwater can be corrosive. And if you have a screen that is not non-corrosive, then you're going to have issues. You're going to have lots of issues. So non-corrosive. Now the size, the openings are sized according to the formation of sand that's in the formation. You know, the size of the particles in the aquifer. Okay, so here, types of screens. This one here does not require the gravel packing on the outside. This one is manufactured with the gravel on the inside. Okay, you can have stainless steel or PVC pre-packed screens. So just to give you an idea of what's out there on the market. So we have the screens, and outside the screen, we're going to put the gravel. Remember that gravel you saw earlier? The purpose of the gravel pack is also to minimize the amount of sand that's being pumped. So it kind of helps us on that screen, to save on that screen. Because if we get a lot of sand every time that pump comes on, and you got all this incrustation on your screen, it's going to minimize the amount of water that you're actually able to pump up that well also. So gravel packs will surround the screen. Again, the main purpose is to keep sand out. It allows larger screen openings when you have this gravel pack in place. It lowers the water velocity in the screen, minimizing the incrustation probability. And all of this that we've talked about, that we've installed in the well, you want to make sure that you are disinfecting it with chlorine. One rule of thumb, or one standard that's out there, is at least 50 milligrams per liter for 6 hours. All right, so let's go back to our little deal here where we have the screen, gravel pack, and you want to then make sure after that gravel has been installed, that's your screen. Remember, this was a water-bearing formation. We're going to disinfect, and the disinfection is not for the aquifer. Is it possible to disinfect an aquifer? Yes, you're absolutely right, not impossible. Because if you remember, some of these aquifers go from state to state. That's a whole lot of chlorine dioxide, ozone, impossible. But what we can do is disinfect what we've put in there to make sure that we're not causing anything harmful.
So I had a question, because you said you put the mud back into it when they're drilling.
When you're drilling, the mud is just used for the drilling process. Usually that drilling mud is forced out. We're going to develop the well to remove that. And that's going to be removed back to the top in the mud pit.
So I was wondering how that affects the aquifer.
Oh, yeah, it can be a major problem. Yeah. Yeah. No, all of that drilling mud is pumped back out. Absolutely. And during the drilling process also, any water should be chlorinated that you're utilizing if you're jetting, you know. Okay. All right, additional parts. We have the concrete ceiling block that extends minimum of 3 feet from the casing in all direction, and it should be, again, kind of sloped downward to minimize contamination. And then we have the well casing that allows the well to breathe as the water level change. We have flow measuring devices, and the casing should extend 18 feet above ground level. Concrete ceiling block, why? Why not steel? Huh? Rust, leaching. And also, what properties do concrete have that steel does not have? Yeah, very porous. So again, as that well is cycling on and off, it can give, more or less. Let that air get out. All right, and we have an air relief valves. Okay. Now, yes, that does have a screen on, and that screen, as with any of your screens that are above ground, must be at least 16 mesh, and that's one of the things that you want to make sure that it is in place, because from time to time it can corrode and you think the screen is in place and it's not. But you should be using a non-corrosive. All right, any questions about the well parts of a well. As far as well sanitation and safety goes, any abandoned well must be properly sealed. Why do you think that's important to seal abandoned wells? To protect the groundwater. Very good part. Absolutely. Any other reason?
Well, if it's a big enough
Safety.
hole, you can actually lose people in it.
Absolutely. Lose people, cattle, anything else. You're absolutely right. So you want to make sure that it's properly sealed. And EPA, there is suggestions on properly sealing abandoned wells. All of our wells should be protected with fences or locked well houses. All of them. Okay, all of that is good for you all. Should have the sealing block, concrete sealing block, the meter, vent, sampling faucet at every well. And we're going to test for bacteriological quality. Now, before you put that well in service, you must pull a bacteria on 3 successive days, and it must be coliform free before you can put it into service. And then we're going to secure sanitary control easement within 150 feet of that public well. Now, do the same regulations apply to private wells? No. So, control easement, 150 feet, all directions from that public well. You must also secure from the homeowners, because again, Tom Place is within that little span of 150 feet. You want to make sure that this is on file at the county courthouse. This 150 feet easement. We want to make sure that we're able to get to that well at all times. Okay, are these abandoned wells properly protected? Absolutely not. Absolutely not. So again, you want to make sure that you're following through on what the rules and regs say as far as properly protecting and sealing abandoned wells. All right, so again, what is this right here? This is our well picture here. We have our concrete ceiling block that extends 18 inches above the floor of natural elevation. Again, properly sloped concrete. We have the casing. We have the pressure cement on that casing. The vent, air vent there. We have the sampling cock, air relief valve, and we have a check valve. What is the purpose of a check valve? Absolutely, keep that water from flowing backwards. Because if we have that scenario happen, then there's a possible cross-contamination, which all cross-contamination should be eliminated on the water side. In addition to the check valve, we may also have isolation valve in case we need to get in there and perform work. Okay. And the water meter, and of course the purpose of the meter is to make sure we can account for the water produced. As far as sanitation continues for your public wells, you want to make sure that there is no source of contamination within 50 feet of that public well. There should be no source of contamination within 50 feet. EPA says you can have livestock and storm sewers, septic tanks, 51 to 150 feet outside of that public well. So because they say 150 feet, your state says what, 100 feet, which is a little more stringent. So there's a little more narrow band there than the 150 feet. And the states have the right to be more restrictive. 300 feet, I can have the underground fuel storage tank and septic drainage fields. This may be something that many states are reconsidering. You look at California, and they had a problem with the underground fuel storage tanks with the leakage of the MTBE into their groundwater sources. And because of that, that additive was removed from gasoline because it was getting into the groundwater. And 500 feet, I can have wastewater wet wells, pumping stations, and drainage fields. Outside of 500 feet, animal feedlots, wastewater treatment plant, solid waste disposal sites, and irrigation with wastewater effluent. So in a nutshell, this gives you the proper distance in order to keep that well protected. Are there any questions on safe distancing? Do you all have any others that are different other than the 150? Yes. What are the other? What are yours? Just so everybody is on the same page in Kentucky. You're going to make me do homework and look it up? If so, I can say I'll come back next time with it because I don't know right now. Maybe I'll Google it. So after we've dug the well, you must develop the well. The purpose of developing the well is to remove anything, as Mary pointed out, anything that we put down in there must be removed. And that is called developing the well, to make sure any of the impurities that we've pumped down during the process is removed. So it removes the fine sand, it rearranges the gravel around the screen, and removes all the drilling mud that we talked about earlier. How do we develop the well? Well, you can use several different methods of developing a well. I guess they wanted to take you through this first of actual pictorial removing this stuff. You can overpump it by 15 to 25%. That would be one way of removing all of that. You can surge it with the agitation of water to force it out. You can use compressed air. You can jet it to remove the drilling mud from the formation wall, or you can backwash it, reverse that flow in order to remove the drilling mud and all. But you must develop it after you've dug the well. After that, you're going to test the well. We're going to test for efficiency. We're going to test the aquifer characteristics. And hopefully most of this have been done at some point where they've actually, did the drill hole. They got the soil type. They got the type of water characteristics of the water in the aquifer prior to going through all of this. And so you know what you're getting before you oops, okay, this water was not good to start with, or I have a problem with it. The capacity of the well, recharge potential, and pump efficiency, all of those things are critical in order to produce the useful quantities of water that you want to, and of course at the type of water. You're going to look at sand pumping to make sure, again, your well screened, your gravel is intact. When you're pumping too much sand, of course, our impellers do not like the sand. It reduces the efficiency of the pump also. We're going to look at improper well development, loss of the gravel pack, large screens or broken or corroded screens, or over pumping as to the reason why we're pumping all this sand. So how do we rectify? How do we minimize pumping sand?
Develop it properly.
Develop it properly. Excellent. What else? Air.
Make sure you have the right screens, the right gravel, the right,
Excellent. You want to repair any deficiency. If you have corroded or screens that are broken, make sure it's the correct size. Excellent, excellent.
So in order to repair things like that, isn't that a pretty major undertaking?
Yes, it is. Just like you saw all the pictorial of digging that well, you got to get back down there to it. Absolutely. It's a major undertaking.
There are
So,
some chemicals that
You can oxidize them. Excellent. And especially if you have incrustation issues, you're absolutely right. And again, you're going to go through those same methods to try to blast or acidize it in order to remove your screen. That's good. What if my pumps are coming on every 15 minutes? Is that good?
Depends on how long they're pumping after they come on. They only pump for a minute.
Yeah, not too good, right? So we're going to look at cycling less, okay, as far as those pumps coming on and on, off and on to help us with the reduction of pumping sand. So good, you all knew that. You can lower the gallons per minute pump rate, you can cycle the pump less, install sand separation devices may be necessary, or correct the problems that you have that may be an issue. Okay, so we got the well in place. We've developed the well. The purpose of developing the well was to remove super. And I asked you all a question just to make sure we're all on the same page. I'm going to give you all a break, although the break is not on the schedule, because I see now we're getting the glass over eyes and all. Let me finish this little component, and then we'll take a break. So we've developed the well. Now we're looking at disinfecting the well. And again, for the most part, we still use SDWA standards, and they say that you can disinfect the well with chlorine at least a 50 milligram per liter dosage. You allow it to stand for 6+ hours. After that, you want to take the back T samples. Now, what will the back T samples show me?
Total contours.
Cool, very good. 3 samples must come back negative. What happens if I come back with a positive? Yeah, got to go back through the disinfection. Yes, sir,
You
Mr.
didn't
Rock.
include flushing the highly chlorinated water.
Yes, you want to make sure that you do that, because that's one sure way I know I come back with a 0 on my coliform, huh? Excellent, excellent point there. Huh?
What are you
D-
gonna do
well-
with that chlorinated water once you get it back out?
I'm hoping 50 milligrams per liter, 6 hours, quite a lot of that probably will have kind of dissipated. What some people do with it is dechlorinate it. What can I dechlorinate it with? Because we know we're not putting any of that back into the receiving streams highly chlorinated, right guys? Say yes. Yes. So what are we dechlorinating it with? What are some methods for dechlorinating if you're going that route? I can use chemicals. Which chemicals? Sodium thiosulfate, sodium bisulfate, sodium dioxide.
What's that dechlor you use, Charles? Captor, dechlor?
Captor, which is, that's a new name, it's a name brand?
Yeah.
Okay, because I'm not familiar with Captor. Okay, so yeah, you can use that. Aeration, okay, add a little oxygen, dissipate the chlorine, excellent. Or long detention time, instead of that 6 hours, longer. That will dissipate the chlorine. So those are all methods of dechlorinating, okay? Pull those samples, no coliform, good to go, okay? After 36 hours of continuous pumping, we're going to pull for physical and chemical analysis. Why are we waiting the 36 hours? Because we want to see what the characteristic of the water in the aquifer. You want to make sure everything that we've added is gone. Now we have the actual water in the aquifer that we're getting a baseline for chemical and physical analysis. Okay, that's a good stopping point. So let's take a 5-minute break. Okay, I have 10:30, 10:35. We will start up again.